In this getting started, we're going to talk about the way to count the total number of items in a sample space and then hopefully extend it to an idea that can be like converted into a formula. When the number of total outcomes is just beyond what we can comprehend because there's thousands of different ways that you could arrange our information, or there's just too many ways to keep track of all the perfect little differences between one situation and another. Case in point, what we have in question 1. There is a formula that we can apply that will do the thinking for us to allow us to then use that information to make larger, broader decisions. It's called the counting principle, and we're going to practice it here. And we're going to show you why it's also important for us to have this idea down. Calculating large sample spaces can present several challenges because it can be too time-consuming or impractical to list all possible outcomes. Even for a relatively small number of options, listing the possible sample spaces can be challenging. I want you to consider this question. How is the organization of our list guaranteeing that we have all possibilities? Well, let's use the first 4 letters of the alphabet, A, B, C, D, and let's list all 3-letter strings. So that's a computer term for like a list of letters, that make not even like a word, but they're just put together into an arrangement. D, B, E, or D, B, A is one of those 3-letter strings. They can be of any length, by the way. Get into some computer coding to see when and how various string sizes matter and are important. You can form these without using the same letter in one string. So here's the way that I've organized the list so far. ABC, ABD, ACB, ACD. Notice that I'm trying to make sure I've got all combinations of B's and then all combinations of what happens if C goes second. A is still going first. Now I want all possible combinations of if D goes second, and then arrange it. Then I change focus. What if B was the first letter? I want all possible combinations of A, and what happens to the other letters? All possible combinations of C as the second letter, and those two. And the same thing for D. It got a little bit disorganized, which is why my question is, how did I organize my list to guarantee I included all the possibilities? I'm going to do a better job right now. In the 4th column, D, there are 6 arrangements where D is the first letter because there were 6 arrangements where A was the first letter and 6 where B was and 6 where C was the first letter. Now, my second letter choice is A, and the second letter, if I put that letter down twice, I can capture all the different arrangements where that second letter shows up, and then the third letter is just whatever's left. So if I go DAB, then I can conversely go DAC. Let's not make A the second letter anymore. Let's make B the second letter. It can happen in 2 arrangements, DBA, or DBC. So that's the scenario where D is the first letter, A goes twice, B, C are the remaining letters. They get their shot one time. B is the second letter, A, C are the remaining letters. They get their shot one time. So I guess of the letters that are left, if D goes first, I could also say there's C in 2 locations. So DCA, DCB. Keeping in mind what goes first, what goes second, and then what's left to go third is the way that I organize this list. And these 2 are not in good organizational structure. This is much better. Much better because I know I've got all A's, but if I go B twice, then I have a choice for the third letter. So it goes like in that grouping. How many different possible strings are there though? Here's the deal. There are 24. The way to tell is I have 1, 2, 3, 4, 5, 6, 12, 18. I can just straight up count them. But there's going to be some thinking that we're going to do to help explain why there's more than or less than or where the 24, the 6 and the 4 in the multiplication process came from. Okay, for each string, how many possible letters could be first? In the first string, there are 4 choices. It could be an A or a B or a C or a D. But once you pick that letter, your second choice cannot come from that list. So then there are just 3 choices left. For example, if I pick A, I'm in the A column, and I have B and C and D as my remaining 3 choices. That's only because I picked A out of the list. If I had gone to a different column, it'd be the same numbers, just they'd be applied in a different way. Same numbers though. So once I pick one of these letters, in my third choice, I only have 2 numbers left. Let's say I picked B. Then I only have C and D left, for example. 4 times 3 times 2? 24. So there are 24 possible arrangements of those 4 letters 3 ways. How many different 4-letter strings, how can your answer to question 3 help you calculate the number of possible 3-letter strings? Well, it's called the counting principle. And the counting principle says in option 1, what's going first? How many options do you have? Once one of those options goes away, then in option 2, you're left with 1 less. By the way, why does the number of choices decrease by 1 each time? Could it be that once a letter is used, the instructions up above said you're not allowed to use that letter anymore to recreate your string? So you only have 3 options left. And 2 options after that, because once you've picked a letter, it's no longer an option for the next event. Use the counting principle to figure out the total number of possible strings. In this case, it was 4 times 3 times 2. That's the counting principle. That's the rule, by the way. I'm applying the counting principle rule. Now, we have our final question. How many different 4-letter strings can you make using the first 4 letters of the alphabet? Okay, so we've opened up a 4th slot. So there's a first choice, second choice, third choice, 4th choice. What goes first, what goes second, what goes third, what goes 4th. In the first slot, you still have A, B, C, D choices. So 4. But after you pick one, now you have only 3 choices left. And then when you pick another, you have just 2 choices left. And then last of all, you're left with the last and final choice. This math is the exact same as the other numbers from up above. So it's 24. I'm not sure why I have let's see, the 24, the number of choices we each will be 4. So if you open up a 4 slot, the counting principle changes slightly too, but this is the same as 4 times 3 times 2, which is the other one. So there's kind of an issue of if you're saying 4 choices, arrange them 3 ways, or 4 choices, arrange them 4 ways, it's the same question. It's literally the same question. You're just cutting one out. Anyhow, this is where we're headed with this level of mathematical thinking. What are the different arrangements of items? That's what we mean by permutations and combinations. How can we arrange the events, the desired outcomes in a scenario, and how many different total outcomes are there? So stick around as we continue to talk about this. There's, of course, more in the Getting Started on the next page. So click on that video, keep learning, and we'll see you in the next episode.